Turn that on. This week we are talking about combining functions. So we have been looking at dealing with functions as a single thing, right? A function takes x's and spits out y's. Now we are going to take two functions and join them together using either arithmetic or another operation called composition that we might get into at the end of class today. If not, then tomorrow compositions, not a new idea, not a thing that you're going to be unfamiliar with, maybe a thing that you haven't seen in like formal sort of math settings, but composition's actually like a pretty intuitive idea. Um, okay, and you have seen some of this stuff at least. These other ideas we'll circle back to later. But the basic ideas are that for function arithmetic, the way we combine two functions is just to use the normal for arithmetic operations, add, subtract, multiply, divide, to combine them together. So if I have two functions and I want to find, say, f plus g, technically what we're doing is defining a new function out of those two, and we call it f plus g. But the reason we call it f plus g is because it takes f and g and pluses them together, right? Like it does what it says it does. So we name it this because that's what it does. So when I write that that equals f of x plus g of x, what I want you to be thinking about is, okay, if these are two given things that I know about, then the way I create a new thing out of them called f plus g is that I just take them and add them together. And the same thing is true for subtraction and multiplication and division out again, but it's the same idea. If I give you two functions and say, hey, what would you get if you add these functions together? You just take them and add them together. And combine like terms where you can combine like terms, and don't combine them where you can't. So, for example, if let's say f was x plus 2 and g is the square root of x minus 5. Then if I want to find f plus g, in broad terms, that's going to look like one thing plus another thing, because that's how the operation's defined. And the things that we're going to add together are f and g using what we know about them. Well, f is x plus 2, and g is the square root of x minus 5. And we're adding. So these parentheses that I've drawn in, those are to help us to remember that we're treating these as sort of one single piece when we do the operation, but the operation's addition, so they're not really doing anything, right? If it was subtraction, multiplication, that kind of thing, they're there to help us to remember to distribute. It's addition, they're not really doing anything, so I'm going to drop those. And then combine like terms. What like terms do we have? 2 and negative 5. The other stuff, x and square root of x, are not like terms, so we just leave them separate. That's it. This is the new function called f plus g that we obtain by taking f and g and adding them together. That's it. Okay? Okay. So let's take 10, 15 minutes. You guys work through the first two examples in the notes. In example one, you've got two functions given, symbolically or analytically, like we just did. I want you to combine them, simplify, so combine like terms. And then for each one, find the domain and evaluate at -2 if possible. And then for example two, you're doing the same kind of stuff, but starting with a graph instead of an equation. Good news is you don't have to do anything different for that. You just have to interpret the graph instead. Yeah, so like, you combine those, you figure out what it looks like in terms of X, like, still you can vary it. Then after you've done that, plug it in. Okay, so.
Okay, so I'm not just talking about the two, but. Okay.
Yeah, that's what happened. That's what happened. Like, I'll take the, okay. All right, quick check to make sure we're on the same page. We've got these two functions, f and g. We want to find f plus g. Somebody set it up for us. X squared plus 3, that's f, plus negative x plus 2. Plus there because the thing said find f plus g, right? So that part's given, right? That's part of the question. Okay, then add and combine like terms. So again, parentheses aren't really doing anything here for addition. Like terms, x squared minus x plus 5. Okay, everybody good with that? Yeah, okay. What about the domain of f plus g? Okay, we could graph it. At this point, you know, we don't have sort of the full set of tools that we will eventually for thinking about domain. There's the graph of the thing. So what does it look like? It's an x squared type function, right? It's been moved around and transformed and stuff. The way it's written, I can't read off that it's, you know, this much to the right and this much up or whatever, because it's not factored out in that way. But it's still related to that. You can, you know, fiddle around with the window if you want to and convince yourself that that continues on to the left and to the right. So the domain here is the whole real line, negative infinity to infinity. If you want to think about it another way, look for stuff that could go wrong, you know. Here, what we need to do is square and subtract and add 5. You know how to do that with positive numbers or negative numbers or with 0. Nothing's going to like go wrong or, you know, break or cause something to be undefined, right? So that's our domain. And then last step, evaluate f plus g at -2. We have found f plus g as a single function. So I can just plug -2 into that. And get 11. Oh, 11. There you go. You can also, or instead, if you want to find f plus g of -2, if you plug -2 into f and plug -2 into g, you get the same thing. So we can either take these two functions and combine them into one and then evaluate, or we can evaluate them both separately and then add those. And you again end up in the same place. Maybe I should write that down. F of -2 would be -2 squared plus 3, so 4 plus 3, so 7. G of -2 and 7 plus 4 is 11 again. So either way gets you to the same place. Now, depending on what we were trying to do, maybe one of these might be more useful than the other. Depending on the information we start with, one of these might be more useful than the other. But you end up at the same place either way, and that's just a property of how these things work. Okay? Everybody feel okay about stuff so far? Does anybody have any questions? All right, I'll give you a few more minutes to continue working on the others. Wanted to make sure we're all on the same page. Mhm. So the last one, the division problem, there's nothing simple, straightforward we can do to simplify that. So just leave it as it is when you know, sort of set the division up. The algebra's harder there, so we'll figure it out later, but not for now. So those are, right, yeah, so it's got to match, power has to match, or it can be like, and then 3 minus 2. So, or 3 minus 2. Okay. Y'all tell me about B. We're subtracting now, same two functions. So the only difference is we're subtracting, yeah. Okay, so x squared plus 3. First set of parentheses really isn't doing anything, right? Minus negative x plus 2. What happens there? Plus x minus 2. And combining like terms, what do you get? Okay, x squared plus x plus 1. So again, it's an x squared sort of thing, right? We could graph it if we want to. Again, we're going to find a thing that looks like x squared that's been moved around somehow in ways that I can't quite read off the same way we would have, you know, with the stuff like last week, because of this, right? Because this linear term is not factored the same way, but it behaves the same kind of way. Short version is that's the domain. And then when you plug -2 in, what do you get? 3? Everybody agree? Okay, great. Okay. How about C? What changes? Multiply. F times G, again, concatenated or written next to each other like that means we're multiplying. Put in a little dot if you want to for emphasis. Now, this is I mean, we saw it with the subtraction thing as well, that second set of parentheses especially to help you remember to subtract everybody. Here we're multiplying a binomial by a binomial. So two terms there, two terms here. The resulting thing we're going to get is going to have four then products before we start combining stuff, right? So when you do this multiplication, we need to do a binomial expansion or a FOIL if you want, or however you do this, if you draw the little box thing or whatever. Everything in the first set of parentheses gets multiplied by everything in the second set. So negative x cubed 2x squared minus 3x and 6. And then, oh, nothing to combine. That's it. No like terms. So we'll just leave it like that. Scoot it a little bit. Everybody okay with that? The multiplication part? Okay. And what's the domain of f times g? Use kind of similar reasoning as the last couple. So I could look at it, actually graph it and see what it looks like and fiddle around and zoom out and whatever until I'm convinced. I could look at this and think about, whether I know how to do each of these operations, cubing, squaring, multiplying by some constant value. I could think about this as being related to x cubed. We know what x cubed looks like. What's its domain? All real numbers. This is just a cubic that's been, moved around and squashed and stretched and whatever else maybe. None of those things restrict or cut up the domain or toss anything away. So the domain here is also all real numbers. And then finally, if you plug in -2, what do you get? I give 1,000 times louder, 28. Okay. I don't actually know. So. Okay, cool. Main thing there that I wanted to point out is this, remind you about this multiplication step. Okay, and then the last one is f over g. F over g. There's me writing out f over g. Been making a big deal about this. I'm not writing them in this time because the fraction bar, you treat the top and bottom as though they're grouped anyway. So I drew those parentheses in a different color because they're always implied. Right? It helps you to actually write them than actually write them, but they're always implied as being there. Now this thing, there's no obvious simplification we can do. Nothing there cancels, nothing there reduces. You may be, if you're tempted to do something like this, don't, because that's not how that works. It's dividing, they have to be factors. So there's nothing we can do to simplify that. So we'll just leave it like it is. That's fine. But now when it comes time to talk about f divided by g, if we start looking at the graph, weird is fine for now. We'll talk more about this kind of thing later in more detail, but what's weird about it? Two of them. All right, it's in two chunks. If I think about the domain thing, we're talking about x values, right? Or think about the vertical line test if you want. If I imagine vertical lines moving along this thing, well, this whole thing appears to only hit it once, right? This whole thing appears to only hit it once. But right here, there's this weird spot where we kind of hop from one to the other. And again, you can, fiddle with the window and stuff all day and, convince yourself what's going on. But there's this weird place where we jump from one to the other. Where does that happen? At 2. Does everybody agree that looks like it's happening at 2? Okay. Well, what happens with this thing if I try to let x be 2? I get 2 squared over negative 2 plus 2, so I get 7 divided by 0. Right? Okay. Fractions, one way to think about fractions is equal sharing. I've got 7 cookies, but no friends to share them with, which is a problem. And again, a deathly allergy to some ingredient of the cookies. It's not a perfect match, but this is a problem. Dividing by 0 is undefined. How do you divide something into 0 pieces? I don't. This is what happens if x is 2. That's that jump that we're seeing in the graph where that gap occurs at 2, and we sort of hop from one branch over to the other one. Again, we'll talk a lot more about that sort of thing later and look at it in more detail. But for now, I just wanted to point out that what happens here is that if the denominator is 0, then when we try to do this division, we get a thing that doesn't work, right? So we took these two things that were perfectly fine to begin with, but when we combine them, something changes about the domain because of division and because of the way division works. So the domain of this is everything except 2. That's how you write everything in the sense of real numbers. The way you write everything except 2 is to do something like that. Open intervals parentheses mean you can get close to that value without including it. So this is everything to the left, but not including 2. This is everything to the right, but not including 2. And then because those don't join up, right, because we're skipping 2 on both sides, the way you join them together, or say like, and or, is with this union symbol, which is, it's not the letter U, but it's like a U-shaped thing. That's the domain. Again, this means everything except for 2, because this happens at 2, and this is a problem. All right, and what do you get when you plug in -2? Which is in the domain, right? 7 over 4. Okay. All right. If you have any questions? Okay. That's function arithmetic. That's how you add, subtract, multiply, divide 2 functions. You do whatever operation says to do. You simplify anything you can simplify. Division's probably the place where we're going to have the least to say about that for right now. And then if we need to think about the domain, the one place where new stuff like additional information gets kind of introduced when we do that is if we're dividing because of this. All right, cool. Okay, well, how do we do this from a graph? Here's F. Here's G. I want to know what F plus G of 0 is. What do we do? What's 0? An X, is it a Y, is it just a circle? Okay, that's an X value. So what can we do for starters? Go find 0. Here it is. And in sort of a bigger sense, here it is. That's x equals 0, that whole vertical line. So go there. That's the only thing I care about now, right? I'm only looking at like that little vertical strip of the graph. That's the only place I'm interested in, because the problem said, hey, figure out what happens when x is 0. Okay, so looking in there, what do I want to find? F What's f when x is 0? 0. Okay, and also I want to find g. What's g when x is 0? 2. And what do we want to do with 0 and 2? Add them together. And what's 0 and 2? Okay, there you go, it's 2. All right. Notice what I'm not doing that I maybe could do here. Did I try to figure out what transformations would give me this graph? I could have. It's a graph I recognize. It's opening down, it's moved up. I could figure that out. The other one's a straight line. We know straight line stuff. I can figure out the slope and the intercept. I could put together equations for these things and then combine them and then plug in. Or, provided I know how to read the graph, I've got an x value. I want to find y that goes with it, but now there are two of them because it's calling these two separate functions, right? It's calling both f and g. So take the x value, figure out what f is, figure out what g is, there you go, and then do whatever it said to do, right? I'm adding here because this said add. Okay? Okay. Tell me about the rest of these then. Yes. This? Yes. That's how function notation works. That part is the argument, the input, the x value. So what is f of -1? -2. And what is g of -1? +1. And what's -2 minus 1? -3. Okay. F times g when x is 1. Here's x equals 1. Here's f. Here's g. What's f of what's f of 1? What's g of 1? What's 2 times 1? Okay. F over g when x is 2. There's x equals 2. What's f? What's g? What's 4 divided by -2? Okay, that's it. Right? So again, this is sort of extending our ideas about being able to evaluate and read a graph, right? We're just doing it twice now and then combining them somehow, right? As indicated, right? Doing whatever it tells me to do with those two values. But we don't have to figure out what the function is or break the whole thing down. We're just looking them up and then combining. Okay, and here's an example of why we might care to be able to do such things. So add, subtract, multiply, or divide two functions together. You can do those then, treating these functions as like objects. You can do those whenever you would need to, add or subtract or multiply or divide. And you learn the same things about the functions that you do normally when you add or subtract or multiply or divide. So, if I take two functions and add them together, what I'm finding is a way to represent the sum of two things. Whether I think about them as sort of separate processes or combine them as one. So here's an example. Suppose that a bike shop named Mike's Bikes has weekly profits modeled by that function P of X, where X is the number of bikes sold during that week. Okay. So that function gives you a bunch of X, Y pairs, right? What do points on that function tell me? What's X? Number of bikes they sold during a given week. Right? And what's Y? Not revenue, but profit. Okay. So what's the difference? This is the 5-cent version of business lesson kind of thing. And this is about all I have to teach you about the subject. What is profit? How much money you made? When we say how much you made, we mean how much you made after expenses. What do we call those expenses? What do we call how much you made before you worried about taking out expenses? Revenue. Total income before expenses. Okay, so you go set up your lemonade stand out by the street in front of the house. You borrow $10 from mom to get lemons and other things, whatever you need to make lemonade. I don't know. This isn't that kind of class. And at the end of the day, you've got, I don't know, $50 in your shoebox, right? Okay, the 50, that's your revenue. That's the total you brought in before you take out 10 to pay mom back, which was your cost. The profit is what's left over, which is 40. How did you find that? Because you had 50 and you took away 10 and you know how to subtract. Okay, so what we have here is a profit function. I even called it P of X, so it'd be easy to remember that it's profit, where the X values are the number of bikes that they sold and P, the Y values, are their profits, income after expenses. Similarly, weekly revenue or total income can be modeled by the function R of X is 250X. So for this one, X values are still the number of bikes they sold. Y values are the total revenue. How would we find cost then? Revenue minus profit. Okay. Tonight then, do that. Revenue minus profit, you have a revenue function, you have a profit function, find a cost function. Find C of 10 and explain what that represents. Find P of 2, explain what that represents. And then think about how many bikes they need to sell in order to break even. And we'll start there tomorrow. Okay? Y'all have a good day. I'll see you then.